Okay, so this lecture is going to be pretty interesting because in this particular lecture we are going to talk about a very essential topic in physics, okay, which is the concept of light as a particle. Okay, so let me give the heading of today's topic. So, light as a particle. Okay, so we have a very famous branch as well as a very essential branch and one of the most important branches of physics, which is quantum physics, right? Which is quantum physics. Okay, and the concept of quantum physics is basically from the is been derived from the de Broglie's hypothesis of dual nature. De Broglie's hypothesis of dual nature. Dual nature of matter. So, in very simple words, de Broglie kind of said, or his hypothesis was kind of that every moving particle has a wave associated with it. Okay. In very simple words, every moving particle has a wave associated with it. Okay. Now, so basically, quantum physics deals with something we call quanta. Quantas are basically packets of energy, or we can say packets of waves. Packets of waves. In very simple words, what quantum physics deals with is that suppose you have a wave. We consider certain groups of waves as a particle, as a packet. Okay. For example, you have a wave, suppose say like this. Okay, suppose you have a wave like this. You have, I mean, two superposition of waves, which results in some kind of this form. What we do is that we consider this as a packet. We consider this as a packet of wave, a packet, right, like this. Clear? So this basically deals as a particle, a packet of energy. Clear? So quantas are basically packets of energy, in very simple words. Okay. So basically, the quantum physics is the study of waves as particles, you may say. Okay. Now, initially, when physics was very dominant in the field of science, physics is indeed very dominant in the field of science, one of the most important branches of science. There was a time when particle nature was not at all important. Rather, particle nature was something which was least considered into discussion. Okay. Everything studied in physics was about waves. For example, light. We have already studied, many topics which are related to its wave nature. For example, refraction, reflection, diffraction, interference, superposition. All these things which we have studied are related to light as a wave. Because initially, we have already studied the Huygens theory of wave fronts. Huygens had already said that light is a wave, and and every wave has a wave front. Waves travel as wave fronts. Okay, light has its wave front. We have also in the +2 level, or you might be studying in +2 level. We will have the chapter of wave optics where we will be studying the derivation of the reflection law, diffraction law using wave fronts. So light was basically considered as a wave. Okay, and we had enormous studies relating to certain topics which are related to light as a wave. Okay. Now, there was a scientist, Max Planck. Max Planck had given a very important observation of light. He said that light, or rather you may say, a ray of light, has particles or has packets of energy which we call quanta, okay. The energy of such a quanta is quantized, we may say. Quantized means it, it depends on certain levels, or it depends on situations. Unless it's disturbed, it remains the same, it is unchanged. Quantized means it remains unchanged unless certain situations are involved. And now these things I'm speaking in very, very simple words. That's why I'm not getting into a deep lecture on these things. Okay. But what Max Planck basically, he discussed that a light ray is a wave indeed, but it behaves as a particle when it strikes some object. He did not say that light has particle nature or light has its particles. He did not go into such deep discussions. He said that whenever a light ray strikes strikes an object, it behaves as a particle. But his theory was not discussed much. His theory was not considered much. So we do not study Max Planck's quantum theory or quantization theory at that point of time. And wave nature of light was still the most prominent topic. Now what happened? There came a very important experiment, by Lenard. Okay, one second. By Lenard. One second, guys. Okay, yeah. So there was a very important experiment by HELLWACH and LENARD, and this is going to be our topic of discussion today. I'm trying to introduce to you the base, one of the most important bases of quantum physics, which started kind of from this experiment of HELLWACH and LENARD. Okay, I will be trying to experiment the whole concept of light starting to being considered as a particle, and why the wave theory came to a failure. Okay, I'm trying to discuss that. So I will be trying to discuss the complete thing today itself. If not possible, I will make one more lecture. So HELLWACH and LENARD'S experiment. Okay, let's see. So the experiment setup, let us first discuss the experimental setup. Then we will be discussing what its target was, what its goal was. Experimental setup. Okay. So he took a vacuum chamber like this. Here was an entry hole. Here were two metal plates, two electrodes, you may say. The wires were connected via a commutator. Okay, a commutator. Let me first draw it. Okay, so this was connected to the positive plate, and from here you have a resistance like this, and here you have a negative plate. Okay, so this is a positive plate and this is a negative plate. Okay, this is a commutator. The commutator basically helps in converting or reversing the direction of current. Now what we do is we basically, okay, so is this much clear? Okay. Now what we do is that we keep this particular plate as a anode. So we connect the commutator like this. So this particular plate is the positive plate. Let us consider at this moment, and it is called the collector plate. It is called the collector plate. Okay, and this particular plate, let us consider as the emitter plate. As the emitter plate. This part is at this moment the anode, and this part is at this moment the cathode. Is it clear? Clear? And this particular setup was made of quartz. The importance of quartz is that quartz doesn't absorb UV rays. Is it clear? And this is a vacuum tube. This is a vacuum tube. Okay. Here you have a commutator C. Let's say here you have an ammeter A, and here is a voltmeter connected. Okay, voltmeter connected. Clear? Now see what happens. Now let us. Now what he basically did was, carefully listen to this. He made light enter this vacuum chamber through this entry. Okay. One second. Let me make this chamber a bit different. Let it be like this. Yeah. Okay. So he made light enter into the vacuum chamber through this entry, and the light to strike on this metal plate. And striking on this metal plate. Now initially what he did was he did not connect this particular cell. Okay, let me keep a key here. Suppose you have a key here, and this key is at this point open. Let's say. So there is no potential across this terminal. Okay. There is no potential across this terminal. Now what he did, he made light enter through this entry into the vacuum chamber, which directly strike this metal plate, and he got some reading in the ammeter. Okay. So what does that imply? So that implies there is a current flow. Across the circuit. When no potential is applied to it. Okay. Let not be a key here, or let me just in simple words say that this cell is still not connected to it. It's a complete circuit, but the cell is still not connected, because if it's not a complete circuit, I cannot explain the concept of flow of current. So let me say that the cell is not connected to the circuit is kept closed. Okay. So whenever light falls on the plate, still when there is no potential across this particular terminal, current is flowing through the circuit, and that particular current is called the photocurrent, because the origination of the current is due to light. Okay, this is pretty much clear. Now as we attach a cell to this particular circuit, now what happens? Now see, this particular cell is to be positive, this particular cell is to be negative. Whenever light falls on this particular plate, a considerable current is observed to be flowing through the circuit. Now the very much logical explanation to this particular concept is that whenever light falls on this particular metal plate, electrons are being ejected from this plate. And since this is a positive terminal, it attracts these electrons, which basically results to the flow of current in the circuit. But we have already seen that even if there is no potential attached across this particular terminal, electrons still flow. Now see, at this particular moment, you have a potential attached across the terminal. These potentials are giving, this potential difference is giving energy to the electron for it to flow in the circuit. It is pretty much logical. But what happens when there is no potential? How can the electron still move across the circuit when there is no potential attached? So that basically means that this light source is providing a certain energy to this electron, which is being converted to kinetic energy of the electron, which leads it to move in the circuit, right? Electrons can move in the circuit only when it has a proper kinetic energy, right? Now when you are attaching potential difference across this particular terminal, then you can say that this potential difference is actually helping the electron to move by providing it energy. But when there was no potential attached, then also the electron was moving in the circuit. That means that this light source is providing this particular electron with a certain amount of energy so that it can escape out from this metal plate. And it has still its kinetic energy to move from this plate A to this plate B and complete the circuit. Is this concept getting clear? That means this light source is having a certain thing which is providing this electron with energy. Clear? Okay, this is the first thing. Achha, now see what is seen in this experiment. Now we have certain graphs related to the experiment, and these observations has basically led to the concept of light as a particle. Carefully listen to each and every point. Now this experiment was done with increasing the potential. Then what we did is that we changed this positive plate to negative plate. We reversed the potential, for example. Let's say we reverse the potential, but so let's say that we apply negative potential. The best explanation is that we apply negative potential to this plate. Okay, we apply negative potential to this place, and we have seen that electrons still flow. Electrons still come out from this particular electrode to this particular electrode. Though this being negative will repel the electron flow, but electrons are still flowing. Photocurrent is still there. Okay, is it understandable? When it is a positive electrode, then the logical explanation to the flow of current is understood. But we are applying negative potential to the collector plate. Electrons are still flowing. The photocurrent is still there. Okay. Then we have changed the frequency. The two changes of this experiment which are important is that change in intensity of light source. Suppose initially we start with a 100-watt bulb, then we move to a 200-watt bulb, then we move to a 300-watt bulb, 500-watt bulb. Okay. And another change was change in the color of light. Color of light means frequency of light. Change in the frequency of light, or rather you can say the color of light. We start with a green bulb, then move to a blue bulb, red bulb, violet bulb, indigo bulb, whatever, green bulb. Okay. So these two changes are what we are basically concerned about through this experiment, or rather Leonard and HELLWACH were concerned about. Okay. Now see. Now this experiment was graphed photocurrent versus intensity. Okay. Photocurrent versus intensity. They kept on changing the intensity, they kept on increasing the intensity of the light source, and they kept on measuring the photocurrent using the ammeter. So their observation was something like this. Let's say, suppose this is a graph. Okay, this is your photocurrent. I am writing it with IP, photocurrent, and this is the intensity of light source. So now what happens is that when you have just provided the light source to the metal plate, a very instantaneous movement, momentarily you may say, or you may in very simple words say without any change in time, you have just applied the light source to the metal plate. So we can say the intensity has just fallen, or you may say that the intensity is just there to be considered. Light source has just fallen on the metal plate and a photocurrent is observed. So basically what happens when intensity is zero, there is no photocurrent. You have just provided the light source, that is some intensity of light is there, and a photocurrent is also observed. A very instantaneous moment. You may say that just light has fallen and just photocurrent is observed. Okay. And we have kept on increasing the intensity and the photocurrent is kept on being observed. Okay, like this. And on taking several observations, we have noticed that the graph comes out to be a straight line. The graph comes out to be a straight line. Clear? Got it? So what is the basic conclusion of this particular experiment or this particular observation? So from here we can say that this photocurrent is directly proportional to the intensity of light. The photocurrent is directly proportional to the intensity of light. Okay, and the thing which I just said, that as there is some intensity, as just the light source has been applied on this particular electrode, the photocurrent is observed. This statement is very important. This, you keep this statement in mind. We will need this statement later. Okay, now he moved on to one more observation which helped him plot the potential current graph. HELLWACH, potential, HELLWACH and LENARD, let's say HELLWACH and LENARD, HELLWACH and LENARD, potential current graph, let's say. Okay. So now what we are concerned about, we are keeping the frequency of the light source constant and we are increasing the intensity of light. We are increasing the intensity of light. Okay. So the graphical explanation, let's, or the graph which came out into consideration. So this was the potential axis and this was the photocurrent axis. Okay. Now, when there was no potential applied across this particular photoelectric setup for experimental setup, there was still some current, as I already said. So let this be the current which was there when the light source was implied on this particular metal plate, but there was no potential across the terminals. Then as you go on increasing the potential, you see the saturation, the current is basically increasing. It keeps increasing till it reaches a certain point where it no more increases. Okay, where it no more increases. Okay, where it no more increases. You keep increasing the potential, but the current no more increases. This particular point is called the saturation current. It is called the saturation current. The maximum photocurrent possible. The maximum photocurrent possible. Now we are increasing the potential. We are increasing the positive potential. Now what we do? Now we start decreasing the potential or apply negative potential on the collector plate. We start applying negative potential on the collector plate. As we do so, we see that the photocurrent has started to decrease. The photocurrent has started to decrease, and there comes a point where the photocurrent becomes zero. There comes a point where the photocurrent becomes zero. Okay, this is the point. This potential is called the stopping potential of the photoelectric setup. Stopping potential, a very important term, stopping potential. Stopping potential is that particular potential applied across the plate which stops the photocurrent in the circuit. Now this is a very general observation which we have taken. Now what we have seen is that now if we increase the intensity of light, suppose we increase the intensity of light, so something of this sort is happening. Okay, it comes here, it starts decreasing, but the photocurrent becomes zero at the same negative potential. The photocurrent becomes zero at the same negative potential. Let this be intensity I1, this be intensity I2. There is a saturation current I1, and for this particular intensity 2, okay, we have a saturation current, let's say IS2. Okay, now this is a very important part. See, you increase the intensity of light. Now in wave optics, or sorry, in wave theory of light, we have already seen that intensity of a wave is related to its energy, because intensity is related to the amplitude of the wave, and amplitude is indeed related to the Energy of the wave. Higher the amplitude, higher the energy. So higher the intensity, higher the energy. Now, what does this stopping potential basically do? In very simple words, let's explain. See, so this is one plate, this is one plate. Here is your negative potential. Suppose you also apply negative potential here. Electrons are being ejected from here. Now, this particular potential, this kind of tries to stop this electron to move from this particular plate to this particular plate, right? This electron, this potential tries to stop this electron moving from this particular plate to this particular. That means, now see, this electron will obviously move from this plate to this plate because it has some kinetic energy. That means this negative potential basically tries to provide a same amount of, or to basically, demolish the kinetic energy which this electron has. If it completely vanishes or it completely obstructs the kinetic energy which this electron has, then the electron won't be able to move from this plate to that plate, right? That means that this potential Vs, the stopping potential has that much energy to provide such that the electron with the maximum kinetic energy stops moving. Now, why I say maximum kinetic energy? Just see. Now, see, this is pretty much, you may think it like this, that when you are, see, light is a particle, light was being considered as a wave. Okay. Suppose you have a metal plate here. I will be explaining everything. Just listen. Suppose you have a metal plate here. There are electrons here, 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 and here. Let's say. Now, what happens is that experimentally, I'm telling first. First, I'm telling experimentally. Experimentally, it is seen that as you keep on decreasing potential, the number of electrons moving from this plate to the collector plate decreases. Okay. As you decrease the potential, apply negative potential or positive potential, which is less. As you keep on decreasing the potential of the collector plate, the photocurrent is decreasing. The photocurrent is decreasing basically implies number of electrons moving from emitter plate to collector plate is decreasing. Now that basically means, see, as you are decreasing the potential or applying negative potential, let's say, a certain number of electrons are not getting enough energy to move from the emitter plate to the collector plate. That basically means that every electron has not got the same amount of energy from the light source, right? Every electron, if would have got the same amount of energy from the light source, then either every electron or a bulk of electrons would have been moving, simultaneously or in a bulk, and then when they will be stopped, every electron will stop at once. The complete photocurrent will be vanishing at once because a bulk of electrons are having the same energy. So when one of the electrons must be stopped, because when one of the electrons falls in a situation when it has no more kinetic energy to move, then every such electron must stop. So the electrons, moving of the electrons must stop in a bulk. But that is not happening experimentally. As you keep on decreasing the potential, the number of electrons decrease, not in a bulk. It decreases gradually. You may consider that each electron or one electron at a time stops moving from the emitter plate to the collector plate as you keep on decreasing the potential. That means every electron has not got the same energy. That is why they stop one at a time. And why do they have different energy? In very simple words, let's say, suppose there is a plate. This is the width of the plate. This is the width of the plate. Now see, this electron will move directly outwards from the plate. This will move outward from the plate. But this electron to move out from the plate, it has to cover this particular distance, and then it can move out from the plate. So certain amount of kinetic energy is being, wasted here. This electron also have to move a certain distance inside the plate and then come out. That is why every electron is not having the same amount of energy when they are coming out from the plate, because inside the plate they need to cover a certain amount of distance. Every particular electron has to, some electrons have to cover more distance inside the plate, some electron have to, cover less distance inside the plate. So the kinetic energy of every electron is not same. This is one thing. Second thing is the electrons are not stopping at they are not stopping at a bulk, they are stopping one at a time. So that basically means every electron has not got the same energy. So as you keep on decreasing the potential, electrons stop one at a time. And there comes a point where you may assume that there is only one electron left which still has the capability to move from the emitter plate to the collector plate, because that particular electron had the maximum kinetic energy amongst all the other electrons. That is the reason why it is still being able to move, because you have decreased the potential such that every other electron is not being able to move. Only that particular electron has the capability of still moving because it has got the maximum kinetic energy amongst the other electrons. And we know kinetic energy has the formula half mv square. So if it has the maximum kinetic energy, it must have got the maximum velocity. So there is an electron which has the maximum kinetic energy, that is the maximum velocity to move amongst all the other electrons. And when that particular electron is also stopped at some potential, that potential is being called the stopping potential. Is the concept clear of stopping potential? So stopping potential is that particular potential, negative potential, which stops the electrons with the maximum kinetic energy, and hence it stops the photon. Okay. Now see what is happening. Now, what is the observed? Now see, he had taken some more intense. He had changed the intensity of light more and more. You would have got some more observations here. Let us say this is I2, this is I3. You had one more intensity here. Let's say I1, where I3 is greater than I2 is greater than I1. But still, the stopping potential of the circuit is still the same. The stopping potential of the circuit is still the same. Now see these electrons are inside the plate. They are initially having no tendency to move. Now when there is still no potential and the light is falling on the metal plate, the electrons are moving. That means that the light is providing energy to the electrons. The light is providing energy to the electrons. Now see, you are keeping on increasing the intensity of light. And since we know that as a wave, energy of light or energy of a wave is basically directly proportional to the intensity of the wave or the amplitude of the wave. Now increasing the intensity of the light as a wave, I am considering light as a wave at this moment. So increasing the intensity of light as a wave must increase the energy of the light wave as well. So as you increase the energy of the light wave, this light is providing a certain energy to the electron. That is the reason why when there is still no potential, the electrons are being able to move. This light is providing energy to the electrons in the plate, in the metal plate, which implies or which leads to the electrons moving or electrons acquiring energy to move. Is it understood? The light is providing energy to the electrons in the metal plate, which the electrons are using to move through the circuit when there is no potential. Now the concept is that even if potential is there or potential is not there, that is not our concern. But the thing is that as you increase the intensity of light, the energy of the light wave must also increase. So the energy provided by the light wave to the electrons in the metal must also increase. So if you keep on increasing the intensity of light and the energy provided by the light to the electrons are increasing, then for every light intensity, the stopping potential must not be same. I have already explained what stopping potential is. Stopping potential is the potential which can provide the energy to stop an electron from moving, the electron with the maximum kinetic energy. Now, if you are increasing intensity, the electron which initially had the maximum kinetic energy must also acquire more energy. So the stopping potential at this moment must not be sufficient to stop that particular electron, right? The stopping potential, suppose when light has intensity, I1, let's say, it provides the electron with maximum uh, kinetic energy, or let us say it like this: when light intensity is I1, it provides electrons with energy h nu, let's say h nu. Okay. Now, as you increase the intensity of light, or let me be more precise, suppose this is it provides an electron with energy E1, let's say. Now, as you increase the intensity of light, since energy of a light wave is associated, it's directly proportional to its intensity, the energy of the electron must also increase. Now, if the electron's energy is increased, then the electron, suppose E, which has its maximum velocity at light intensity I1, and it also has a maximum velocity at intensity I2. Let this be V2 max, this be V1 max, but V2 max is now greater than V1 max, right? Because as the energy has increased, the kinetic energy of the electron with the maximum kinetic energy, which was supposed to have the maximum kinetic energy, has also increased. So in very simple words, the maximum kinetic energy of the electron has increased. If the maximum kinetic energy of the electrons has increased, then the stopping potential must also change to negotiate the kinetic energy. It can't remain constant, but it is remaining constant experimentally. So from here we get a very important conclusion that, now see, stopping potential is remaining constant. What does that mean? That means the energy of the electron is not associated with the intensity of light. Experimentally, energy of the electron is not associated with intensity of light, right? With intensity of light, because if that would have happened, then the stopping potential must have changed. What does that basically imply? That basically implies that the energy of light, indeed, because energy of light is what is being transferred to the energy of an electron. Light is only providing the energy to the electron. The energy of light is not associated with its intensity. But what we had studied in wave mechanics or wave theory of light, energy of light is associated with its amplitude, with its intensity. But experimentally we are seeing that when light is striking an obstruction, when the light is striking a metal plate, when the light is striking a surface, the energy it has at that particular instantaneous moment is not at all associated with its intensity. What this conclusion is doing is that it is indicating towards a failure to wave explanation, to a failure to wave theory of light. Is it understood? This particular concept is basically indicating towards a failure to the wave explanation, wave theory of light. Because wave theory of light says energy of the light wave is associated, is proportional to its intensity. Experimentally, we are seeing the energy of the electron which is being ejected out from the emitted plate is not at all associated with the intensity of light. Because the intensity of light is not being able to change its energy. What does that basically mean? That basically means intensity of light is nowhere associated with the energy of light itself. That means light cannot be considered as a particle when it's striking the surface. Sorry, light cannot be considered as a wave when it's striking the surface, because if it would have been a wave, then its energy must have been associated with its intensity. It is not happening. That means light is playing the role of a particle when it is striking a surface. Or rather, in very simple words, or in more deep words, we can say that light is not only a wave. Light is behaving as a particle. Light has its own particle property, which is being experimentally observed under this particular photoelectric effect. Is it being cleared? Initially Max Planck had said that light behaves as a particle only when it strikes some particular surface. But here we are being able to see that the energy of light is not associated with its intensity. So that basically means that light has a particle nature in it. It is not only behaving to be a particle, it is having some particle in it. It is having some particle nature. It is not only playing the role of a particle when it's striking a surface. It is indeed having a particle nature, an independent particle nature in itself. Got it? Achha, let this lecture be up till this much, guys. In the next lecture, we will be studying about the concept of what happens when you change the frequency of light, keeping the intensity constant, and what happens. And then from that particular lecture, we will be moving on to the concept of Einstein's explanation to the photoelectric effect, and why did he get the Nobel Prize? What was his statement? How bold his statement was, that he has become so famous giving this particle light as a particle, giving the explanation to photoelectric effect. We will also study the Millikan's experimental verification of Einstein's theory of photoelectric effect. Okay, I hope you enjoyed this lecture, guys. I will be trying to bring out more lectures on physics on my channel. Maths lectures, I am not being able to upload maths lecture on my channel at this moment, but I will surely be trying to do so itself. So meet you guys in the next lecture.